Our topic for the next few lectures is probability. In many ways, discrete probability is an application of combinatorial counting, which was already a challenging enough topic, but one that most of us don't have a lot of preconceived notions about. But when it comes to probability, on top of the combinatorics and counting, we also have to contend with our own intuitions. And at least for me, my intuition about a lot of probabilistic ideas turns out to frequently lead me astray. And so I think it will help to start today with some very basic definitions that we can build on when we talk about more complicated probability topics in the near future. To talk about probabilities, the first thing we need to establish is what are the possible outcomes that could occur whose probabilities we are considering. So we begin by establishing a set S. This set has to be non-empty so that something can happen. And then we have a function that gives us the probability of each outcome. And we need that all of the probabilities are between 0 and 1, and that the total probability over all of the outcomes is 1. One of the random events that we think about most often is rolling a 6-sided die, where the set of possible outcomes is that the die roll could come up 1, 2, 3, 4, 5, or 6. And if the die is fair, then the probability of each of those outcomes is 1/6. So all of the probabilities are in the range 0 to 1, and if we add them all up, we get a total probability of 1. We could make it slightly more complicated and think about rolling 2 dice. And here we have a choice as to what we want the outcomes to be. The most natural choice might be to have the total showing on the 2 dice as our outcomes. So then we would have outcomes ranging from 2 to 12, and we would need to figure out the probability of each of those outcomes. But since the next bit of notation that we're going to introduce gives us a way of combining different outcomes into events, we can actually make our lives easier by instead defining the outcomes to be the ordered pair of rolls of the 2 dice. And then when we introduce the notation of events, we will be able to easily calculate the probability of each of the possible totals. We've defined our outcomes as pairs of the value on the first die and the value on the second die. And this makes it easy to specify what is the probability of each outcome. So the probability of rolling a 2 and then a 3 is just 1/6 for the first die and 1/6 for the second die, so 1/36 in total. We'll talk more about multiplying independent probabilities later, but we could get to the same function p by counting the number of pairs. If we have 6 possibilities for the first element and 6 possibilities for the second, then there are 36 possible ordered pairs. And since each of the dice is equally likely to come up with each of its faces, each of those 36 possibilities is equally likely. And so to have 36 probabilities that are all equal and sum to 1, they must all be 1/36. But we can also very much have events whose probabilities are not equal. If the random outcome we're trying to model is the probability of Steph Curry making a 3 in a game, then we might have the outcomes of the shot was made or the shot was missed, and the probability of those outcomes might be 40% and 60%. So now that we have a definition of a sample space with outcomes and probabilities, we can think about more complicated events that are combinations of outcomes. We define an event as some subset of the outcomes. So if our outcomes were 1 through 6, we could define the event of rolling at least a 5 to be the subset of S that contains the elements 5 and 6. And to calculate the probability of an event, we add up the probability of all of the outcomes in that event. So here we're defining P to also apply to sets of elements, and we get the probability of a set by adding up the probability of all of the elements in that set. So we can think of the event as a collection of outcomes, and the event happens if any of the individual outcomes happen. With our rolling 2 dice example from before, if the outcomes are pairs of a roll for the first die and a roll for the second die, then we can think about the total on the 2 dice as an event, where the event of rolling a total of 4 includes the outcomes 1, 3, 2, 2, and 3, 1. And so we can add up the probability of those individual outcomes, which are each 1 over 36. So the probability of the event rolling a total of 4 is 3 over 36, or a 12th. Here, we're asking the question, if we toss a coin 4 times, what's the probability that we get at least 3 heads? So I have not yet defined for you the sample space, and so it's worth pausing for a moment to think about how would you set up the sample space here? What are the outcomes? What is the probability for each outcome? And then what outcomes do we need to combine into the event that will give us the probability we're looking for? A natural thing to try first would be to have the outcomes be the number of heads that came up across the 4 flips, and that could range from 0 to 4. And then our event would be the outcomes 3 or 4, and we could add up the probability of those 2 outcomes. But from here, it's not immediately obvious how to figure out the probability of each of the outcomes. And so if we choose a different set of outcomes, we can make the initial task of figuring out the probability function easier, and then we'll have a little bit more adding to do in figuring out the probability of the event. If instead we define the outcomes to be lists of 4 heads or tails in order, then we know that each list is equally likely because the coin is fair. And so we just need to count the total number of lists, and the probability of each list occurring will be 1 over that number of lists. And we know how to count lists of length 4 with 2 possibilities for each element. That's 2 to the 4th, or 16. So each outcome has a probability of 1 over 16. And now we can define our event to be the set of all lists that meet our criterion of having at least 3 heads. And there are 5 of those lists, so our probability is the sum of 5 1/16. So we get a probability for the event of 5/16. Perhaps I should have talked about this before erasing the board, but one thing that last example shows is that when modeling a physical process as a sample space in our language of probability, we might have multiple reasonable choices for how to describe the set of outcomes or the events that we're interested in. And how we make those choices can have a big impact on the difficulty of the probability calculations we end up having to do. As a general rule, try to make the basic set of outcomes as straightforward as you can so that we can assign probabilities correctly. That will mean that in general the hardest part of the problem becomes counting the number of outcomes that make up our event, but at least that sort of combinatorial counting problem is one that we already have a lot of practice with. If we want to combine multiple events, then we can think about the union of 2 events, which is the set of all outcomes that are in either of the events. So the union corresponds to either event happening. Or we can talk about the intersection, which is the outcomes that are in both events. And so the intersection of 2 events corresponds to both events happening. And we can relate the probabilities of the union and the intersection to the probabilities of the individual events using facts that we already know about intersection and union of sets. We already proved an extremely similar looking property about the cardinality of sets, and this proof is extremely similar, except that rather than just counting the number of elements, we are adding up the probabilities for each element. If we add up the probability of all of the outcomes in set A and the probability of all of the outcomes in set B, then for the outcomes that are in both A and B, they will appear in both of these sums, and so the things that are in the intersection of A and B will be added twice, but the things that are in the symmetric difference of A and B, that is, they are in A but not B, or B but not A, will appear in one of these sums but not the other. And so we will have added all of the things in the symmetric difference once and all of the things in the intersection twice. But that gives us the same sum as the right-hand side, where here we will have added all of the things in the intersection of the 2 events once, and then we will add all of the things in the intersection of the 2 events again when we add the union, and then the union will also add in the probability of each event in the symmetric difference once. And so by combinatorial proof, we have a relationship between these probabilities. And this is particularly useful if we want to calculate the probability of either of 2 events occurring. We can add up the individual probabilities and then subtract the probability of the intersection. Or if we want to calculate the probability of the intersection, we can add up the individual probabilities and then subtract the probability of the union. If we roll six-sided dice, then we could think of the sample space as a set S, which is lists of length 6, where each element is 1 through 6. And then each of these events has equal probability. So we just need to figure out how many events there are. Well, we have length 6 lists and 6 options for each element of the list. So we have 6 to the 6th possible lists. And so the probability of each individual outcome is 1 over 6 to the 6th. So then event A includes all of the outcomes where none of the elements of the list is a 2, and we know how to solve that counting problem. That gives us just 5 possibilities for each of the elements of the list, and so that means that we have 5 to the 6th outcomes that meet the criteria of event A. And so event A has 5 to the 6th outcomes, each of which have a probability of 1 over 6 to the 6th, and so this gives us our probability of event A. If only 1s or 2s were rolled, then we know that there were only 2 possibilities for each element of the list, and so we have 2 to the 6th possible outcomes. C is the event that we only roll even numbers, so that gives us options of 2, 4, and 6 for each element of the list. And so we know that there are 3 to the 6th total lists that meet those criteria, and so we have 3 to the 6th over 6 to the 6th as our probability. We could similarly specify more complicated events that would require us to do more complicated counting like we have done on previous exercises and reviews. But we can also now combine some of these events using our knowledge of the relationship between intersection and union. The intersection of sets A and C is that we didn't roll any 2s and we only rolled even numbers. So here we know that all of the rolls must have been either a 4 or a 6. So that gives us 2 possibilities for each element of the list, and we should get the same probability that we got for B. The union of events B and C is that either only 1s and 2s were rolled, or only even numbers were rolled. So this includes 1s, 2s, 4s, and 6s. And so now we have 4 possibilities for each element. The intersection of events A and B is that no 2s were rolled and only 1s and 2s were rolled, which leaves us with only the events where a 1 was rolled. And so this requires all 6 elements to be a 1. So we have only a single outcome in this event, and so the probability of this event is just 1 over 6 to the 6th. And now if I were to ask you more complicated questions about, for example, the sum of the 6 rolls, you could turn those questions into events that collect some of the outcomes in the sample space, and then add up the probability of those outcomes. Or in some cases, you could formulate your event as the union or intersection of other events that are easier to count. And either way, you could come up with the total probability for events that involve more complicated conditions on the collection of outcomes.